Hi, everybody. I wanted to talk to you really quickly about the Bernoulli soda bottle experiment. I want to discuss a little bit about the observations from the experiment video and then talk to you about the analysis of the data. So first, you noticed that the height of the top of the water column in the soda bottle was located at about 250 millimeters above the tabletop. The location of the hole on the side of the bottle where the stream would be exiting the bottle was located about 125 or 126 millimeters above the tabletop. And then, of course, you noticed as the hole diameter increased, the landing location of the stream increased as well, from about 140 millimeters out from the base of the bottle to a maximum of about 230 millimeters out from the base. So as the hole diameter got bigger, the landing location moved further and further away from the base of the bottle. So I put together some data about the experiment, and it's shown here on this slide. That's an awesome diagram of a soda bottle, as you can see. The landing location I've marked as X on my diagram. There was about 124 millimeters between the height of the hole and the height of the water level when the water started exiting the bottle. The hole itself was 126 millimeters above the tabletop. So you should have been able to predict the landing location of the water stream first by determining what the velocity of the water stream was from the hole. And that's you using Bernoulli's equation, which is, remember, a conservation of energy equation. So that says that the total energy at the top of the fluid from the pressure there, as well as the gravitational potential energy of the fluid column and the motion of the fluid there, that sum is equal to that same sum at the exit port. We assume for this problem that the pressures at the top of the fluid and at the hole are the same. They're equal to atmospheric pressure. And we also assume that the velocity at the top of the column is 0. When we do that, we end up with that thing we call Torricelli or Torricelli's theorem, where the velocity is really the same as the velocity of a solid object that you might drop from a height equal to the height of the top of the fluid. So when you do all that, you're able to come up with a velocity for the fluid exiting the bottle of about 1.6 meters per second. And once you know how fast the water is exiting the bottle, then you can apply some projectile motion concepts to the water stream, where that velocity, that exit velocity, is the horizontal velocity of the stream. And of course, the stream is not accelerating in the x dimension, only in the y dimension. When you do this math, you end up with a predicted landing location for the stream of about 249 millimeters or 250 millimeters. And remember from the video that the longest landing location and that was for the largest diameter hole size, that longest landing location was about 230 millimeters. The failure of the theorem to predict the actual landing location of the water stream coming from the soda bottle is because the theorem itself is about conservation of energy. And remember this idea where the total energy, the total mechanical energy of a system at one position being equal to the total at any other position, that assumes that the system is closed and that there's no work being done on the system by external forces. But I think what's happening with this exit port is that the port itself is holding up the fluid as it's trying to stream out, and it's doing negative work on the system when that's happening. And so there's a loss of energy in the system at the exit port. And I think that loss of energy is greater when the exit port is smaller than for exit ports that are larger. So in other words, when the exit port was increased in diameter, the landing location of the stream came closer to the one predicted by Bernoulli. So anytime you're thinking about analyzing data where you're making assumptions, for example, about conservation of energy, and the analysis of the data does not match experimental results, you can assume there's probably some loss in the system.